In today's explanation, we're going to explore how particles behave in gases and how their movement results in the creation of pressure. Imagine we have a sealed container filled with gas particles. These particles move freely and randomly in all directions, bouncing around unpredictably. Whenever a gas particle hits one of the container's walls, it rebounds and continues moving in a new direction. Even though each individual particle is extremely small, it still exerts a force on the wall every time it collides with it. And because pressure is defined as the force applied per unit area, or in simpler terms, the total force divided by the area it is acting on, these tiny collisions collectively generate measurable pressure inside the container. The overall pressure depends mainly on two key factors: the number of collisions happening in a given time and the amount of energy involved in each collision. We can use these two principles to understand how temperature, concentration, and volume each affect the pressure inside a gas container. First, let's consider temperature. If we heat the gas, we're adding thermal energy into the system, which means the kinetic energy of the gas particles increases. As a result, the particles start moving faster. Because they are moving faster, they collide with the container walls more frequently and with greater force. Since both the frequency of collisions and the force per collision increase, the pressure also increases when the temperature is raised. Next, we have concentration. If we increase the number of gas particles within the same fixed volume, in other words, if we add more gas without changing the container size, then we have a higher concentration. With more particles bouncing around in the same space, there are naturally more collisions with the container walls, and therefore, the pressure increases as well. Finally, we come to volume. If we reduce the size of the container while keeping the number of particles the same, we effectively squeeze the gas into a smaller space, which means there are more particles in each unit of volume. This is the same as saying the concentration has gone up. Because the particles now have less distance to travel before hitting the walls, the number of collisions rises, leading to an increase in pressure. So, as the volume of a gas container decreases, the pressure inside increases. This is a key concept in understanding gas behavior. Now, one final point to mention is that not all containers are rigid and fixed in shape. In some situations, such as with a balloon, the container is flexible and capable of expanding or contracting. In these cases, when the gas inside gets hotter or the number of gas particles increases, the pressure may not rise dramatically. Instead, the balloon might simply expand in response to the increased collisions or higher kinetic energy. In reality, what usually happens is a combination of both. The volume increases as the balloon stretches, and the pressure also increases slightly because there's a physical limit to how much the balloon can expand. The important thing to understand is that the relationship between pressure, temperature, and volume becomes a bit more complex when you deal with expandable containers like balloons. You do not need to perform any calculations here. Just remember that the behavior changes depending on whether the container is rigid or flexible. And that wraps up today's explanation. Hopefully you found it helpful, and we look forward to seeing you again next time.